Except for submarines and seaplanes, marine vessels are designed to function afloat upright in still water. Have you ever wondered why a rock weighing just a few ounces will always sink while several tons of steel shaped like a ship will float? Well, the reason in one word is displacement. Before we try to explain displacement, if you think that gross tonnage is the weight of a vessel, you are wrong and stop associating gross tonnage with weight. Gross tonnage is a volume, and we will cover that in another course. Back to displacement. In the picture on the right of this slide, first we see a container filled with water and a gray object weighing 7 pounds. When the object is immersed in the container, some water spills out of the container. We can say some water has been displaced from the container. If we collect the displaced water in another container, we will see that the object displaces its own volume of water. The volume of water displaced by the gray object is just 3 pounds. That is less than the 7 pounds weight of the object, so the object sinks. So, let's look at the question about the sinking rock and the floating ship. The rock weighing just a few ounces will always sink because the weight of the volume of water displaced the rock will usually be less than the weight of the rock, so the rock sinks. The ship weighs several tons, but because it is shaped like a ship, that is, it is hollow and relatively long and wide, its weight of the water displaced by the ship is equal to or more than the weight of the ship, so the ship will float. Here is another simplified way to look at sinking or floating. On the left we see the 1 pound weight of the sealed empty bottle/ship acting downward. The weight of the volume of water displaced by the whole bottle is 10 pounds and shown as acting upward on the bottle. And the empty bottle/ship floats. In the middle we loaded 8 pounds of cargo and stores in our bottle ship. So now we have 9 pounds acting downward, and the weight of the volume of water displaced by the whole bottle is still 10 pounds, and shown as acting upward on the bottle. And the bottle/ship weighing 9 pounds is less than the 10 pounds of water displaced and still floats. On the right we loaded 11 pounds of cargo and stores in our bottle ship. So now we have 12 pounds acting downward, and the weight of the volume of water displaced by the whole bottle is still 10 pounds, and shown as acting upward on the bottle. and the bottle/ship weighing 12 pounds exceeds the 10 pounds of water displaced and sinks. In the previous slide, the arrows we saw pointing downward represent the force of gravity. Some people call it gravitational force. And the arrows we saw pointing upward represent the force of buoyancy. A body in water will sink until the buoyancy force matches the gravitational force. If the body cannot displace the weight of liquid equal to its own weight without submerging, it will continue to sink. If the body displaces a weight of liquid equal to its own weight before submerging, it will float. Let's look at buoyancy in a little more detail. We've already seen that buoyancy is an upward force. The force of buoyancy is considered to act vertically upward through the center of buoyancy. This center of buoyancy is the center of the underwater part of the hull. Straight away we must try to visualize that the center of the underwater part of the hull changes every time draft changes, and we will soon see that center of buoyancy will change every time the ship rolls. This slide tries to demonstrate that the center of buoyancy changes as draft changes. In the top part of the diagram, imagine a ship with no cargo and with a draft of 4 meters. The center of buoyancy will be the center of the underwater hull, shown as the light blue dot. We then load cargo and the draft of the ship changes to 8 meters. The center of buoyancy moves to the new center of the underwater hull, shown as the navy blue dot. In the bottom part of the diagram, we see the ship upright and heeled over. When the ship is upright, the center of buoyancy is at the light blue dot. When the ship is heeled over, the underwater hull becomes the portion colored green and the center of buoyancy will to the center of the green portion and is shown as the navy blue dot. In an earlier slide we said that the force of buoyancy is considered to act vertically upward through the center of buoyancy, and the center of buoyancy is the center of the underwater part of the hull. Considered to act means for mathematics and diagrams we consider the force of buoyancy to act through the center of buoyancy shown in red. In fact, the force of buoyancy acts upward on all of the bottom of the ship, that is shown by the arrows with the BS. Ignore the Kansas, Miss and GS for now, we will cover that in another lesson. Now let's talk about gravity in a little more detail. We've already seen that gravity is a downward force. The force of gravity is considered to act vertically downward through the center of gravity. In the previous slide we said that the force of gravity is considered to act vertically downward through the center of gravity. Considered to act means, for mathematics and diagrams, we consider the force of gravity to act through the center of gravity shown as G. In fact, the force of gravity acts downward on all over the ship, that is shown by the arrows. A ship floats when the force of gravity acting on it is balanced by the force of buoyancy created by the displacement of the water. The weight of the water displaced is equal to the weight of the ship. The weight of the ship is often referred to as displacement. Displacement and draft have a direct connection. As weight of cargo, fuel, stores, etc. is added to a ship, the draft and displacement increase. As weight of cargo, fuel, stores, etc. is removed from a ship, the draft and displacement decrease. The triangle in this slide is the Greek letter for D called delta. We use it to represent displacement in formula, equations and diagrams. I think this is because draft and depth also start with D. B by itself in formula, equations and diagrams is the force of buoyancy. G by itself in formula, equations and diagrams is the force of gravity. When the vessel is floating upright in still water, the force of gravity and the force of buoyancy are equal and opposite to each other and acting on the center line. One definition of stability is the ability of a floating vessel to remain upright, or return to the initial upright position when disturbed by forces acting on it. For example, held by wind or waves.